Today we're going to finish section 10.4. We left off, the last thing we had done was something called mean absolute deviation. And let me just remind you real quick of the table that we set up for that, because it's directly related to what we're going to do for the next one. So we found the average. We'd actually had it on a previous problem. It was 19.9 as our average value, the mean. And then we took the difference between that mean and each of our individual values, ignoring signs. We took the absolute values. We added all the absolute values divided by 7. Okay, so we're going to jump back to the other type of deviation. And it's actually called a standard deviation. And it involves a topic called variance. So you'll notice that these are some similar steps. Step number 1, find the mean. We've already done that for our data set because we're going to do the same data set in a minute. The second thing is to subtract the mean from each number. We already did that. Now we did absolute values for that, but the reality is that step 3 says that we're going to square them all anyway, so we can use the absolute values that we already found. Okay? So we're going to square all the differences. And then steps 4 and 5 look just like on the mean absolute deviation. We're going to add them up and divide by the number of values. So the only step really that's new is this one right here, which is the squaring the differences. That gives us variance, and then to find standard deviation, we take the square root of the variance. And you'll see where standard deviation is used in the next set of information that we're going to move on to in just a moment. So we are going to use standard deviation. Okay, so we're going to find the variance for this. The first parts are exactly the same as this table, so I'll let you copy your table. I'm going to highlight and copy my table. You can actually use all the absolute values if you want. You don't have to go back and actually subtract them and care about the signs, okay? So you're going to create the same table we had before with each of the values subtracted from the mean. That's steps 1 and 2. Find the mean. We did that before. The mean is 19.9. And find the difference each of those is away from the individual data values. And after we do that, what we're going to do is we're going to take that quantity of the previous column and we're going to square it. So grab a calculator if you don't have one. So after you rewrite this table, you're going to take 1.9, 2.1, all the way down to 7.9, and we're going to square each of them. So the first one is 3.61. The next one is 4.41. And there are 2 of these that are the 2.1s in a row, if I remember. Yep. I have another 4.41. And then we have, my lines are a little bit off. Let me slide that up a little bit. I have 2.9 squared, so 8.41. I have 10.1 squared. That one's going to be quite a bit larger than the other ones. 102.01. I have another 1.9 squared. I already did that. That was 3.61. And then the last one is 7.9 squared, which is 62.41. So that's step 3, squaring each of the values. Step 4 and 5 are just like we did with mean absolute deviation with the green pieces. We're going to add them all together. That's step 4. And then we're going to divide by 7. That's step 5. So we're going to add 3.61 plus 4.41, another 4.41, and then 8.41, 102.01, 3.61, and 62.41. Total that I got was 188.87. Does that look okay? Okay. And then we're going to take that 188 0.87 and divide it by 2. And I don't mean 2. I don't know why I said 2. 7. Divide by 7. And we get, again, just 1 decimal is fine. If it asks you for more specifically, you can do that. If I did 2 decimals here, I'd get the 9 and the 8, which means this is actually just 27, because I'm going to round to the nearest decimal, so 27 or 27.0 if you wish. Variance, that's what this is actually called. You can write out variance like VAR if you want. Oddly enough, variance's notation is either S squared or sigma squared. That's the actual notation that's used.
Can you call that bigger? What is that sigma?
Yeah, it kind of looks like a scripty R.
Oh, okay.
That's kind of what it looks like when you do it. But you can write the word variance. You don't need to use that. But those are both notations for variance. There's actually another notation for mean as well. We've used the one with the bar on the top of it. Another notation is the letter mu. You'll see that used if you were to take a statistics course, actually. You'll see those come up. All right, and then our last piece on this one is to actually find the standard deviation. The standard deviation actually is S. That's nice, right? Because what we're going to do is we're going to take the square root of the variance, which was S squared, which is the square root in this case of 27. So this is variance right here that we're taking the square root of. And then the square root of the 27 with 1 decimal. We'll do it. It's 1 decimal, so it's an approximation, but it's 5.2. Yep, Abby.
Like, I guess in a real world, like, why do these numbers matter? Like,
I'm going to do an examples of those, so hold tight to that question. It's a really good question, and it's exactly the next topic. Okay? Okay, so we're going to talk about a type of distribution that uses the mean and the standard deviation, and that type of distribution is called a normal distribution. Now, not everything is distributed as a normal distribution. That's just not true for everything. Typically speaking, you need large numbers of data sets in order for them to be approximately normal. But with a very large data set, it will often be a normal distribution. For example, you've seen in the store when you go and you buy, say, a box of tricks. It'll tell you on the bottom of the box of tricks how much the weight is of the tricks inside. You know what I'm talking about, right? Does it for canned goods, boxed goods, all kinds of things. Now, the reality is it may or may not be exactly that weight. There's sort of this level of inaccuracy that's acceptable, and for them to still tell you that it's 11 ounces. Right? So it really might be 10.9 ounces, or it really might be 11.2 ounces. And within a certain level of accuracy, we're okay with saying that it's 11 ounces. The boxes of cereal would have this normal distribution because they're making them in such high quantities at a time. So this is actually a distribution that looks like a bell-shaped curve. So when you just say grading on a curve, this is actually what grading on a curve means, and it's not what you mean when you say it. When you say it, you mean add a bunch of points to everybody's score to make the top score 100% or something of that nature, right? It's not what grading on a curve is. Grading on a curve means finding the average score and making that your 75% score, essentially. And then making it evenly distributed around them so that you'd have the same number of A's as you do F's. Now, that might be beneficial if the mean is low. But if the mean is really high, this could be very detrimental. The mean could actually be like 85%, and then it's scaled back, and that's now your C range. You would not like that very much, right? So this actually looks like a bell-shaped curve. I'll draw it here in the next slide in a minute. Do I have space on the next one? Oh, I'll draw it here, but let me draw it here first. So it looks like this. Okay. The mean is the value in the middle. So this one is the X bar. And then what happens is that in equal increments on either side, we go 1 standard deviation away. So this is 1 standard deviation away. And then we do 2 standard deviations away. And then we do 3 standard deviations away. So why? Well, this part right here that's 1 standard deviation away, contains 68% of the data. Off the top of my screen, but it's written down here. This is called the empirical rule. 68% of the data is in that spot. You know what, I might have enough space to pull it down here, at least pretty close anyway. If we go out 2 standard deviations, I'll change color just to so hopefully show that it's doing that. If we go from here to here, so that I'm 2 standard deviations out, I actually have 95% of the data. So 95% of the data is within 2 standard deviations of the mean for a normal curve. And if I go out 1 more, we'll go with blue, to here, the 3 standard deviations out, it's nearly all of the data. It's 99.8% of the data that is within 3 standard deviations of the mean. That's where your box of cereal needs to be. It needs to be within 3 standard deviations of the mean, because that's almost all the boxes of cereal, right? That would be our goal. So I'm going to show you how we use the empirical rule because it's really very handy, and we'll do it with an example problem. As we're looking at normal distributions, you're going to draw a curve on every single problem. I do realize that some of you probably can reason through this without the curve because you're probably thinking the curve in your head. Just draw it for me. That way we're all on the same page, okay? So we're going to start with the normal curve. It does not have to be a perfect drawing. Just an approximation is fine. And then the piece in the middle is the mean, and the problem typically gives you that piece of information. So this problem says, assume a normal distribution. That has to be said for you to draw the curve, okay? If it doesn't say there's a normal distribution, then it's not a normal distribution problem. You can't make that assumption. This is assume a normal distribution. The average phone call in a certain town lasted 8 minutes. So this average phone call bit is the mean. So this right here is 8. And then it tells you it has a standard deviation of 2 minutes. So we're going to take our diagram and we're going to mark out 2 on either side 3 times because that's our 3 standard deviations away. So we're going to go from 8 to 6. I don't mean 6 there, I mean on the other side. How about 10 on this side? 8 to 10, 8 to 12, and 8 to 14. The other side is my 6, and then my 4, and my 2. So I mark off the 3 standard deviations in both directions. Everybody good so far?
So your standard deviation is how many you move for a certain deviation?
It's how many you move for a certain percentage of the data.
Okay.
So ours is 2 away is going to give me 68%. So this is telling me that 68% of the phone calls are between 6 and 10 minutes. Okay? This picture is telling me that 95% of the phone calls are between 4 and 12 minutes. And it's also telling me that 99.8%, nearly all of the phone calls are between 2 and 14 minutes. That's what this picture says with the data we're given. Okay? So we're going to use that to answer the question about part A, where it says what percentage lasts between 6 and 8 minutes. Now, 6 and 8 minutes is here. So I'm going to use some shading as I do these for my 6 and 8 minutes. So 6 to 8 minutes is here. That's not 68% of the data. Say it louder for me, Nathan.
30.
It is 34.
34.
It is 34. 34 is the right number. Okay, so Nathan, where'd you get 34?
It's half of 68.
Yeah, so it would be 68 if it went from 6 to 10, right?
Yes.
But a normal distribution is symmetric. It's symmetric around the mean. So half of the 68, namely 34, would be on the left side between 6 and 8, and the other half between 8 and 10. So this ends up giving me 68 divided by 2, or 34%. So our answer is 34% of the phone calls are between 6 and 8 minutes. Okay, are we good with that? Okay, I'm going to you can redraw the picture on the next page because yours switches pages. I'm going to paste mine and take off the green because it doesn't fit my picture anymore. All right, so the next question asks us about things that are less than 4 minutes. So less than 4 would be shading all over here. And not just down to 2, but all the way basically back to 0. But in terms of my picture, I don't have 0 marked, so I'm just stopping the shading at the edge of where I've stopped my graph, okay? Evidently, I didn't get that piece moved down, did I? Or that one. All right, those look all wonky now. Okay, any ideas about how I can find that piece of red that's shaded in? There's more than one way to do the problem. Asia, do you have an idea?
Take the 99.8 and do something with it.
Okay, you're close. It's not the 99.8 that I want, though.
95.
It's the 95. So right now, here's what I know. Well, I know that all of this piece right here is 95, right? We agree with that? That piece is 95. So it might be helpful then to think about what is just on this side of it. If that whole piece is 95, how much is the part I just shaded in yellow? Okay, so 95, and it should be halved, right? This is my yellow part. It's, what did you say, 47.5. So the part in yellow is 47.5. How can I use the fact that the part in yellow is 47.5 to find the part in red?
Is it again half of that one?
Nope, not half. I'm just throwing out random numbers. This isn't working at all. How about, let's talk about this part of the graph then. Do purple. How much is over here in my sort of boxed in purple triangle shape-ish? How much?
50%.
50%. How come?
Because it's half of the graph.
It's half the graph.
50 minus the 47.5.
There you go. So we would take 50% minus the 47.5. And what would we get? 2.5.
I did that in my head.
I'm so proud.
Why is it
was great.
50% if the whole thing is 99.8?
The whole thing's not 99.8. The area between 2 and 14 is 99.8.
And the other parts of the other.
There are some little tiny-ish pieces, right? It's like 0.02 out here on these little edges added together because it has to be 100% of the data, right? There's always an outlier option or at least possibility. Asia?
So if we look at it that that top percentage is 95, couldn't we just realize that it's like 5% left and then
Yes, you
divided
could.
by 2 is 2%?
You're exactly right. That's another option. So another way of doing it is, remember I said at the very beginning of this problem, there's a couple of really good ways of doing this problem. You could look at these outer edges and say, okay, well, the whole graph has to be 100%. So the part that's in yellow and the other half of the side that's not in yellow, but it would be, the equal part would be the 95%. And so we could take 100 minus 95 and divide by 2 to get the same 2.5%. And in fact, that's actually the one that I have written down in my notes. And that works too. Yep. Okay, what do you think? Okay, we got one more. We got one more. Oh, that wasn't what I wanted to do. Oh, that's definitely not right. Okay, let's try this. All right, we are going to find the percentage of phone calls that last longer than 12 minutes. So longer than 12 minutes, where's that going to be? Where am I going to shade? 12 to the right, yep. This yellow piece over here now. So this is my 12 to the right. How am I going to find that? It is. It's just the other half of the same picture, right? It's still 2.5. Yeah. So this is the same 2.5 from the previous problem. It's just the right-hand side instead of the left-hand side. Okay, let's do another one, and it has an extension part to it as well. These are IQ scores. IQ scores, standardized tests are normally distributed, by the way, folks. Did you know that? Yeah, standardized tests are a normal distribution kind of thing. IQ tests are a normal distribution because they're a standardized score as well. So the mean IQ scores for 1,500 students is normally distributed with a mean of 100 and a standard deviation of 15. So as soon as we saw normally distributed, it tells us I'm going to do what? Yep, I'm going to draw a normalized curve. And I'm going to mark the mean. What's my mean?
100.
100. And then I'm going to use the standard deviation to find the three pieces on either side. So what was my standard deviation? 15. So 115. Yeah, I'll do the other side second. 130 and then 145. And then on the other side, 85, 70, and 55. Okay, is the picture part okay? Okay, so we're going to use the same picture for all the pieces of this particular problem. So I'm going to copy mine right now. It says we want the IQ to be between 85 and 115. Okay, so 85 to 115. What would that percentage be? 68. Yeah, it's okay. The next one's 95 is what you're thinking. So this is 68%, but that's not quite what this question asked. What did the question ask? How many students? Not what percentage.
Then 1,000 times 0.68.
Right. So we take our number of students, 1,500, times the decimal that corresponds, or you can do it in proportion form if you wish. So 0.68. And then we need to make sure when we give our answer, if it gives us decimals, that we round things to appropriate values because we don't have halves of students. How many students is 68% of these students? 1,020 students. Okay, so this is sort of a separate step at the end because of the question that was asked. The last questions asked about percentage of phone calls. These questions actually ask about numbers, not percentages of students. Okay, so let's do this one. This one says over 145. Close.
0.1.
Okay, so why is it 0.1?
Because 0.2 is outside both sides, so
Yeah.
it's half.
Okay, so Madison, you're right. This piece right here that goes between 55 and 145, that's the 99.8. What that means is that these outer pieces that are left over have to be the remaining part of that 99.8%, which would be in fact 0.2%. But I only have the right-hand side shaded, right? So this will be equivalent to 0.1%. That's not 1%, that is 0.1%. How do I find the number of students that that corresponds to? Yeah, so with 1,500, what's the value I'm going to be multiplying by?
0, 0, 0,
Close,
or 0, 0.
001. So if you're struggling because it is a weird number, remember you're moving the decimal 2 to the left. So in order to move it 2 to the left, I need 2 zeros to move it past. What does this give you? Yes, so 1.5, which would mean we have 2 students. A 145 IQ is very high. Okay, very, very high. 2 students. All right, I think this is the last one of these. Oops. I was trying to move my screen and I inadvertently moved the picture. So, okay. This one says scores between 70 and 145. So 70 to 145 would be all of that. And again, there's more than one way to do this particular part of a problem. In particular, notice that they're not equally shaded on each side of the mean, right? So be careful about that. Be careful about looking at it and thinking something's equal and it's not. So ideas, what would you do first?
You
Asia, do you have an idea?
I said just just find what you know within the secondary standard deviation, and then you can just half that through, or the second one.
Okay, so for this half of the data, which I think is the part you're describing over
Yeah.
here, so what would, this is 2 standard deviations away. What's the 2 standard deviation number? 95%. And we would half it, yep. Okay, so we also need the right half though. So what are we gonna do to get the other half of this picture, or the other side of this picture? So instead of having 95, now we need the 99.8 because it's 3 standard deviations away. And yeah, divided by 2 again. So I think you told me this one was 47.5. What about the 99.8 divided by 2? 49.9. Great. If we add them together, what do we get? 97.4. Now, if we were asked for percent, we'd be done, but we're not. We're asked for numbers of students, so what will we do? And the 97.4 is a decimal value, instead of a percent, is 0.974. What would you get? What do you get? 1,461 students. So what you see happen a lot with normal curves, to kind of go back to Abby's question of how do we see this used, one of the ways you're going to see this used is in standardized testing in your schools. Like it or don't like it, if you're part of the public school system, you're going to be using standardized tests. And as a parent, I get back standardized tests for my kids every time they take a state test. Every time they take a NOEA test, we get back these standardized scores, and they're always looking at normal curve distributions. So that's actually where I personally see them used, and where you're probably going to see them used professionally the most. All right, the last thing in this section has to do with percentiles. Percentiles are also used with standardized testing. Percentiles actually show a person's score or value of something relative to other scores. For example, a score in the 90th percentile means that 90% of all other scores would be lower than that score. It doesn't mean you got 90% right. Okay? So what ends up happening is that you can't get 100 percentile on anything unless you are the absolute top person to score on any of it, and then 100% of every other score will be below you. So you see a lot because that means nobody scored exactly the same as you did, and that's highly unlikely, to be honest, right? So you don't see 100 percentile types scores practically ever. You're looking at things that are 99% and below. Percentiles are used, like I said, with grades, standardized testing. Another place that you will probably all at some point see them used is in some kind of a growth chart for some child that you either are taking care of or that you have, as your child. They like to do head circumference, they like to do height, and they like to do weight. And they like to see that those are all in the same percentile. So my little one that's out in the hallway, the one that's, the tiny one, right? She has her doctor's appointment today. They'll be checking her height and her weight. Her height is in like the 60 or 70 something percentile. She's pretty tall for her age. It means 70% of the people will say 70. 70% of children her age are shorter than her. Okay? But her weight is in like the second percentile. Right? She's very, very tiny. And so one of the things they watch for her is they want to see that her percentiles are staying close to what they were before, that any of her medications she's on are not interacting with that. Another percentile thing that has been a part of my life specifically is that when we adopted my son, who's 14 from Ethiopia, he had a larger than normal sized head circumference. There's no way of knowing what happened, but it was probably the case because we had records an early part of his life in Ethiopia, the first 4 months. And then there was a jump between month 4 and month 7, and between that jump, the head circumference went way up. He probably fell or was dropped. It's probably realistic. And so we had to go through all this extra testing and things for MRIs and stuff like that to see that his brain was not damaged and everything before we even got to bring him home. But when we came home, They would monitor his head circumference very closely because they wanted to make sure that his head circumference was not growing at an extended rate, right? They wanted to make sure that it was slower than normal growth, even though his head circumference was a larger than normal head circumference size. It also kept him from walking very early because his head was heavy. He had to have hard to walk. So he was like 18 months old before he could walk. Yeah. So interesting things, but those growth chart things are really important markers for your pediatricians. They look at those and they pay a lot of attention to them to try to make sure that kids are sort of in that healthy weight and height ranges, and then head circumference when those random things come up. All right, so we're going to take a look at an example from a standpoint of academics for percentiles versus class rank. So class rank is something you're probably familiar with, right? Where do you fall in the list of, highest to lowest GPAs in your class? Junior was ranked 50th in his graduating class of 325 students. Liz was in the 75th percentile. So ranking and percentiles are related, but they're not telling you the exact same information at face value. Question is, which student had the higher GPA when they graduated? So we get to decide. We either need to change Junior's 50th ranking into a percentile, which we can do, or we need to change Liz's percentile into a ranking. So which one would you like to do first? We're going to do them both just so you can see how both of them work, but Junior. Okay, so for Junior, he's the 50th person out of how many? 50, I should have written it beside it. He's 50 out of 325. So how many people are actually below Junior? How would I find that out? Say it again. Subtract. Yeah, so we'd have 325, minus the 50, and you're exactly right, Braden, it's 275. There's 275 people below Junior, right? So we take our 275, we divide it by the 325, that's the total number of people, and this will create his percentile in terms of his ranking. So 275 divided by 325. And then I should probably say, to turn it into a percent, we'll actually multiply it by hundreds. Let me write that in there. .86 is his percentile. Is that okay? So compare his 84.6 percentile to Liz's 75 percentile. Who has the better GPA? Junior. So the answer to the question now is that Junior has the higher GPA. So that's how we can take the ranking and turn it into a percentile. Just because we're going to do the other half of it so you can see how it works too, in case that were the desired approach or you thought of it first or whatever. So we're going to take Liz. And Liz has a 75th percentile, right? So we're going to take the 325 students and multiply it by the 0.75, kind of like what we were doing on the previous problems with the GPA, or the IQ scores. That's what it was, IQ scores. So if you do 325 times 0.75, we're going to round, it has to round for it to make sense. So rounded, it's 244 students. What about these students? They're below Liz. Now that does not mean her class rank is 244. How do you find her class rank? Close. So, well, let me write it that way first. So the 325 minus the 244. The 325 minus 244 will be her class rank. That won't tell you how many people are above her because she's one of those. I just was thinking about that when I said close. You're actually right. So 325 minus 244 is what? 81. Is 81. So there's 80 people above her. So she's ranked 81st, right? Compared to junior who's ranked 50th. So both of these should result in the same answer, and they do. Junior is still ranked higher, right? Or junior's GPA is still a higher GPA than Liz in both of those ways of doing it. Any questions on that?
On the first way that we did it.
Yeah.
Did you just divide 50 by 325 and then it's like 15, 14 something?
Subtract. Yes, you could do it that way too. Exactly. Yeah, there's more than one way to do them because of the balancing of what's going on. Yep, you're right.